academic use cases meeting from SiLA. And I mean, the origin of this meeting was that in the past, we figured out that the demands in the academic environment are actually quite different from the demands in companies, especially in terms of using legacy devices and small budget. And since in the original, like in the SiLA consortium, it is carried by hardware providers, which do not have an intrinsic interest in supporting legacy devices and keep them running long time, we thought it would be nice to have a special meeting for academic, well, to look at automation from an academic point of view. And after the last meeting, there was quite some feedback and people found it very useful. So we organized the second meeting. And to not lose more time, means we have to finish by 5, I would like to present the first speakers today. So that would be Tessa Habich and Ferdinand Lange. So they are from the University of Hannover, from the Technical Chemistry Department. And yeah, they are talking about automation for chromatography. Is that right? Or have you changed? Still
no, that's
valid? Okay. So yeah, Ferdinand, just go ahead.
Yeah.
Perfect.
Okay, can you see our screen?
Yes.
Okay, perfect. Yeah. Okay. Yeah. Thank you for introducing us, Tim. We will talk about today about our SiLA use case that we have here in our institute, which is the digital integration of a periodic counter-current chromatography system with SiLA 2 using Docker on gateway modules. We are part of a larger project group, and Lukas from the University of Munich also presented their use case last time. And yeah, the larger project group is called Digitization in Industrial Biotechnology, where we try to make bioprocess development cycles more efficient. And the part that Jülich does, they do the phenotyping of the microorganisms, and they screen for mutants that produce a certain protein that we want to have, and then they pass on the best mutant to Munich, where they do the where they find out the best cultivation parameters, and then cultivate the microorganism, and then they pass on the fermentation broth to our institute, where we do the downstream processing. And today we will focus on the chromatography part of the downstream. Yeah. So first, I will talk about more of the hardware part, the periodic counter-current chromatography system, which I will just call PCCC from now on because it's shorter and easier. And then after that, my colleague Ferdinand will talk about the server part. So first, what is chromatography? I'm just doing a short slide on this. It's basically a separation method to isolate target molecules from a mixture of different proteins. The target molecule is interacting with the stationary phase, which is the blue part in the figure on the right. And then the target molecule kind of binds to the stationary phases on the chromatography column or membrane adsorber, and then after that it gets eluted by a shift of pH or a different molecule that replaces the target molecule on the stationary phase. And behind every stationary phase you can put a detector where we have different detection methods. Either you can detect the proteins by UV, or if it's a fluorescent protein, then you can also have a fluorescent detector behind it. So why do we use the continuous chromatography for protein purification? Firstly, because it's more efficient, we have a higher product yield, and we use less buffer. Also, we can use the binding capacity better of the membrane adsorbers or the columns, because we can load them up to their maximum capacity without having any product loss, because we start or we use the column switching strategy with the periodic counter-current chromatography, where we first load the membrane adsorber, so the first one, and then if that one is starting to get full, then we can see the signal rising at the detector behind it, and then we switch the breakthrough onto the second membrane adsorber, so that all the product that breaks through gets loaded onto the second membrane, and then the membrane gets fully loaded, and then after that the feed switches to the second membrane, so we don't have any product loss. But for that we need real-time data, because we need to have for the dynamic control we need to have the real-time data, which is also one of the reasons why we wanted to digitize the whole system, so we can purify the proteins more efficiently. This is the basic infrastructure of our PCCC. It's a modular system, so it's also really easy to add new modules, or to replace some modules. We just recently added a fluorescence detector, and then just integrated it into our whole system. So on the left side you can see the lab device itself, so the PCCC, which has a Modbus server that controls all the pumps and the valves, also the light sources and the fraction collector. We also have 4 spectrometers behind every membrane adsorber, and they are connected to the Odroid, so to the tiny computer via USB. The Odroid enables the SiLA communication, and it's based on the gateway module that Ferdinand will talk about later. And it also runs Docker containers. So the first Docker container that's running on there is the spectrometer control, which you can see on the left side, on the right side of the figure. The spectrometer control is reading all the current values from the spectrometers and then passes them on to a pipe, so that all the current values are in the pipe, which then the SiLA driver can use and can read from the pipe. The SiLA driver itself is also on a Docker container, which is then easier to integrate if you wanted to have, or if you want to build a new chromatography system, then you can just download it from our driver server, and it's easier to maintain. The SiLA driver itself is controlling the Modbus server, and so with that we can control all the pumps and the valves and so on. So now I will, after I gave you a short overview about the hardware and the chromatography system itself, Ferdinand will now talk about the SiLA server and software part.
Thank you, Tessa. I am Ferdinand Lange, and I will talk about the server infrastructure and the software infrastructure. First of all, I'll give you a little overview. All of our laboratory devices are based on our gateway modules. The gateway module is a little device between the SiLA communication and the device communication. And we are running a minimalistic Linux on the device to enable the Docker environment. Each of our SiLA services are provided by a Docker container, and for the PCC example, as Tessa mentioned before, we have running 2 containers, one for the SiLA driver and one for the spectrometer controlling, and one of them has additional blockly-based method editor to write new or modify methods that are controlling the PCC. On the server side, we developed a web application based on ASP.NET with the Blazor framework. This framework allows us to easily develop server-side interactive web UIs to give an overview of what the PCC is doing, or to control the PCC. And the second goal of this application is to provide a device manager with the task of handle all the Docker connections and the SiLA connections, and also to provide a web UI for the maintenance of Docker containers to start, stop them, and update them. All of our SiLA clients and drivers are developed with a C# SiLA Tican framework. This gives us a nice and easy opportunity to develop them. Each of our software projects are stored in our GitLab repositories, and we configured GitLab pipelines to automatically build our projects, and this provides us a deployment-ready environment. With this, I mean we can easily install or flush a pre-built Linux image to a new hardware, and then swap the Gator module or the Untitled himself in the laboratory, and we have only to run the SiLA driver with the provided Docker container. Here we can see a screenshot from our PCCC web UI interface, and we can see the status of the device in this corner and some information about the currently running method. We can start and stop the method or set some options. In the middle and on the bottom of the page, we have an overview of the spectrometer values, and in the graph on the downside this page, we can see the spectrometer values from the last from the current experiment on the time scale. Here can we see the rising blue curve and from the spectrometer one, for example. This is a screenshot from the device manager, and we can see our PCC is connected, and it provides some device information, for example, the IP address or the container information, which container is running. We can stop them or start them again, make an update, and this provides some configuration information and logging information as well. In our institute, we have multiple SiLA environments. One of them is our main laboratory, and we have some for the testing and the development. And we run in the problem that we don't want to store the connection information neither on the device themselves or on the server application. And to solve this problem, we are using following method. Our laboratory device make an DNS lookup to himself and get the corresponding laboratory IP address as a text record back. Now our device can request a connection based on the IP address to the device manager, and if the device manager accepts this connection, then he adds the device in the list and create a Docker SSR tunnel to control the SiLA containers. After the SiLA driver is running, the SiLA discovery can find this device and create a SiLA device connection. In the near future, we are planning to implement and connect a database to our infrastructure to provide a way to automatically store the measurement and other data that are provided by our SiLA drivers in a FAIR data format. FAIR stands for findable, accessible, interoperable, and reusable. And we long-term goal is to provide a way to analyze our experiments and improve them. In the end, we want to say thank you to our colleagues, our group leader Sascha Beutel, and our former colleagues, and of course our colleagues in the big project in Jülich and Munich, and of course our project sponsor BMBF. And thank you for your attention, and if you have any questions, we would like to answer them.
Yeah, thank you, Tessa, and thank you, Ferdinand, for the very interesting talk. Yeah, data infrastructure is very interesting to me, especially the Docker containers. I've got quite some questions, but I think for the sake of time, maybe we should, unless there's somebody with a very urgent question, we should just go to the second talk and have the questions all at the end to not lose track of the time. Are there any questions which have to be posed right now, or? Okay, then yeah, thanks again, Ferdinand and Tessa. Then I would like to present Adam Wolf as the second speaker. So Adam is from Austria, from Takeda, and he will talk about the robotization. I think most people in this call know him anyway, so no need to present. And yeah, Adam, go ahead.
All right, start to share my screen. Thanks a lot, Tim, for the invitation and for organizing this event. So I will talk about a concept rather than a concrete application example of SiLA. And to start, I would like to present something what we call hierarchical decomposition of laboratory workflows. The motivation behind this is it lets us organize the automation pyramid, the different levels of the technological stack into a hierarchical structure and assign them to certain logical levels of the workflow itself. It's important to mention that the focus of my work and my presentation is robotics, more specifically sample transportation. So in that regard, the highest level is the workflow itself, the whole process. It can be an assay, an experiment in the laboratory, which consists of certain steps of liquid handling, analytics, and again, the most important aspect in the context of this presentation, the robotic sample transportation. So that task you can divide further into subtasks, such as picking up the sample carrier, putting it on some storage and placing it. And further progressing downwards towards the low-level layers, we reach the level of what we call the robotic action primitives. So these are elementary units of activity, robotic activity, for which we are working on semantic representation, parameterizable units representing some meaningful outcome from the robotics perspective. So below that, the lowest level is that level where the lab automation process controller don't need to get insight to, so to say. It's the robotics motions, primitive motions, really linear type or circular type motions. And to further concretize the scope of this concept, I want to introduce a certain type of robot, a mobile manipulator, namely. These are becoming to get quite widespread in laboratories for sample transportation purposes, mostly samples on standard carriers such as SBS format microplates. The robots use a certain type of parallel gripper to manipulate these. And there are different anatomies. You can use a smaller footprint mobile platform and put a SCARA robot, a 4 degrees of freedom robot on top of it. or you can use something bigger and then put a 6 or 7 degrees of freedom arm. What's in common is that they all use some sort of simultaneous localization and mapping technique for autonomous driving. And for fine positioning, they need an additional perception element because the accuracy of the platform itself, of the base itself, is not sufficient enough. In most cases, they use vision. But still, it's necessary to teach the robots in relation to the optical markers. And how it's done is first the operator has to, or the integrator, the user has to drive manually the robot in front of the device, so next to the workstation, and make sure that the camera sees the marker. So then the coordinate transformation between the camera and the marker can be determined by the computer vision algorithm. And then the operator has to move the arm manually, either by hand or by jogging the arm to align the end effector frame with the handover frame. And then since the robot's kinematics is known, that is based on the geometry and the joint values, the transformation between the camera frame and the end effector frame are known. And then the transformation between the marker and the handover site can be defined. So that's what we ultimately need for the robot to be able to load the sample afterwards autonomously. What we propose is to make this setup process plug and play, so to not require teaching manually, but to request the device vendor to put the marker on a predefined position on the front side of the device to make the device compatible with this framework, and also to prescribe the frames and positions in relation to this marker attached coordinate system, so that the robot then can use these handover positions and intermediary positions to actually operate the device. So for that, we propose a representation layer to store those information. And this aligns with the digital twin approach. A digital twin is namely a digital representation of a system comprising the relevant properties and behaviors for the system to operate and to optimize its operation. What we propose is to have different digital twin instances for the different components of the system. So instead of taking the usual traditional approach of storing every robot-related information in the robot's control system, we attach the information to the component. So, for example, in the case of devices, the vendor has to specify what type of robotic action and task has to be fulfilled, what type of workpiece needs to be loaded. So in the case of pick and place, it's mostly SBS microplates. And then the previously mentioned coordinate frames and positions. Additionally, for the robot to plan a collision-free trajectory, also the collision geometry of the device can be defined. So these are parameters that are valid for all of the same model of devices, but that may differ are certain geometrical imperfections. So the possibility has to be kept open to calibrate those positions. And those are then parameters that correspond not to every instance of the same model, but to a certain device. On the robot side, you have to define the capabilities of the robot. So what type of gripper it has, what's the working envelope, what's the reach, what's the maximum payload, and how many degrees of freedom it has. So SCARA robots, for example, have 4 degrees of freedom. That means they can't roll and pitch, only rotate along the vertical axis. Whereas in some use cases, it's important to be able to get to every possible orientation. And there, 6 or 7 degrees of freedoms are needed. Also, the robot has some own frames, home position for when it moves, for example. And then also another type of category to which we assign a digital twin is the room itself. The room has namely a map that is generated when the setup process takes place, and then kept updated with sensor input from the laser sensor, so that the robot is able to navigate autonomously and also avoid obstacles, dynamic obstacles, as such. Similarly, in the case of collisions, you have the base collision geometry of the device stored in the device's digital twin, but you can overlay live 3D point clouds on top of that based on the robot's sensors, and then that gets stored in the room's digital twin instance. So that's an example of using this framework for the specific use case of sample transportation. And to make it possible, we have to combine a bunch of technologies. So throughout these layers of the automation pyramid, so to say. And the goal is to use as many standardized solutions as possible, existing well-established solutions, beginning from the high-level process representation, how the workflows are programmed by the laboratory expert. And there are already examples with the business process modeling notation, the BPMN. And there are research work with biologics-specific representation possibilities. And then towards the lower levels, the robotic actions can be also encoded in different levels. In the literature, I listed some papers from researchers from the SiLA Institute of the Rostock University. And then on the technical side, the interoperability and the device communication has to be implemented, obviously, between the different components and different layers. And for that, SiLA is a very suitable solution. Whereas on the low level, you need some robotics system, robotics middleware to integrate the different components of the robot system, the sensors, the actuators. And for that, the robot operating system is a good solution. And this lower level is where we put our contribution, so to say. The laboratory automation plug and play robotic action primitives will be a library of parametric elemental robotic actions, parameterizable library. That's the subject of future work. A follow-up paper will elaborate this. And this current concept proposal is going to be released as a preprint paper probably next week. I'm happy to share that with you if you are interested in more detail. And then more in the future perspective, we can make the system capable of incorporating more advanced use cases. So not just pick and place type sample transportation, but also manipulation of complex objects based on advanced perception. And also not only with the wheeled ground-bound mobile manipulators, but maybe quadrupeds or drones as such, they open up literally new dimensions that also require, from the digital twin perspective, new layers of representing the relevant information. As I said, the most important aspect in regards of the technological implementation is that we use standardized solutions, and that's why SiLA is one of the most important enabler technologies in our point of view. So here's a list of relevant literature. If you're interested, I'm happy to share this presentation, the slides with you. You can look into it. And with that, I thank you for your attention, and I invite you to the SiLA Robotics Working Group meeting, which starts at 5 p.m. We can continue the discussion there. And Tim, for your information, I made you co-host. So
Okay.
You should be able to continue in this room, even if I
Thank you. I mean, I definitely want to join the other work group as well, because it's quite interesting. I do have quite some questions, especially about the latencies, because the question is, I mean, we had a simulation when we thought about, for example, if the robotic arm and the end effector should be two different SiLA devices or should act as one SiLA device. And then we were always worried that the latency of the SiLA communication is too slow if you have very tight connections.
Yeah.
But
so,
yeah.
So that's an important aspect, that we don't want to control everything with SiLA, every layer.
Exactly.
So the bottom layers probably better to keep on the robot controller level.
Yeah, it's a question where to make the cut. But yeah, maybe we can I will join your robotics session afterwards. Can you post a link to the robotics session into the chat?
Sure. Yeah, I can do that.
Okay. And Lara has an urgent question. Lara?
I think it's Mark.
It's Lara Robot. It's Mark. It's not Lara. Sorry. But where is he?
Well, he's in his office, but probably has some
not
problems
speaking.
with Google Meet.
Okay. Well, maybe he can ask later. I mean, he knows you, so he won't be shy to interrupt you, Stefan. So maybe we can then just go to the last talk today from Stefan Mark from Kiwi Biolabs.
There he is.
Here he is. Hey, Mark.
Hi. I was really having trouble, as Niklas said. Can you hear me?
Yeah, low, but yeah.
But yes.
I'll shout. So my question is regarding your primitives. So how primitive are these? So is it just really the coordinates of a position, or is it already a kind of abstraction? That is something that was not clear to me.
Mm-hmm. So yeah, as I said, that's subject to future work. The primitives are defined in the previously mentioned coordinate systems, but they are in fact robotic action primitives. So like a simple action of approaching something, or a rotating action of turning a knob, pulling out a drawer of a device, opening a door, those types of, also to make device interactions, physical device interactions possible.
Okay, I see. Yeah. And about so if you move a container, for example, it would be like a gripping primitive, like a lifting primitive, like movement primitive. So
exactly. Yeah.
Okay, maybe we should leave the discussion for the robotics work group, because otherwise, I think, Mark, you came late because we have to finish in time at 5. So I would like to introduce Stefan Mark as last speaker today. Yeah, go ahead, Stefan.
Okay, let's see if this works. Okay. You probably see my screen now? If not, okay.
Yeah.
So I'm Stefan. I studied mathematics, and currently I'm employed in the Greifswald working group as a PhD. And within the Kiwi project. And my main task is to optimize our robotic platform. So we have a platform in Greifswald. And yeah, that's my main task, but it's also planned to extend this framework to Berlin. So, and there are, as you probably can see, several devices on this platform in Greifswald. I'll give you a list later. And in the middle, there's a robotic arm to physically connect these devices and transport stuff from one to another. And in Berlin, there is a mobile robot, like Adam showed you. These are the pictures of the two. So on the left, you see our Lara arm. It's a quite strong robotic arm, which can carry these microplates. And the right one is SiLA, so mobile lab assistant, which can go around the lab, which is in this case necessary because, as you can guess, the devices are straight all over the laboratory. So you need some kind of mobile robot. Okay, so what we do in these laboratories is bioprocess development, similar to what Tessa and Ferdinand described. And these are all, so Greifswald is focused on enzyme design and Berlin is focused on cultivation. And for the details, you have to ask Mark or the people in Berlin. So from an automation perspective, it's only some experiments which involve several devices and a lot of steps. And this has to somehow be automized because these experiments typically take 1 day, 2 days, and no one wants to do that by hand overnight and over the weekend, if not absolutely necessary, of course. So this is a list of our devices. For all of those, I wrote SiLA servers, in our case, SiLA Python. So we have storage, this can turn. We have 3 cytomods, which integrate shakers for growing cells. We have a centrifuge. We have 2 plate readers. We recently got a second one. A barcode reader and a pipetting robot. And this is a little gripping tool, which is needed for technical reasons, and a dispenser. And yeah, as I said, we definitely need some central scheduling software to run these experiments. They are typically, the last one was 16 plates or 29 plates, which go around the devices, go to the incubator, get measured, get back, get measured, get back, and so on. So this platform has been running for a while, since 2012, I think. So there was a solution. And what you actually need is, at first, of course, you have an idea what experiment you want to run. Then you somehow have to describe this process. Something like Adam mentioned, BPM, Camunda, PAML. In our case, we took another solution. This has to be parsed by the computer to a workflow and then executed via some automation software. And in 2020, so when I got employed, the status was that there were several vendor-specific integration solutions. So for every device, there is another software on the computer to control this individual device, and commercial scheduling software for larger experiments. And the problem with this is that these specific softwares are quite complicated. So effectively, Mark was the only one knowing how to operate all these. So if anybody wants to do something, he has to go to Mark, and they have to do it somehow together. This software computed bad schedules, so it ran into deadlocks. It sometimes incubated for 2.5 or 3 hours when you told it to incubate for 2 hours, which is of course suboptimal. And you can't interact with the process. So you can plan it, or at least tell it to do a schedule, and then start it, and then it runs. You can't change any parameters, you can't add steps, and when it runs into an error, it stops and doesn't adapt in any way. And if there's any device which is not supported by this particular software, you're stuck. In our case, it was a dispenser. So you simply can't use it. And you can't use your devices in a way that is not supported. So if you want to do some extra steps the device is capable of, you want them, but you can't because the scheduling software has no option for it. And yeah, these problems were so severe that this platform was not used very often, although it would have been quite useful for certain projects. And that was why we decided to automate it with SiLA, because if you have something like a universal client, which can control all devices via the same interface, then it's easier to use. I'm not sure if the SiLA manager by Lukas Bromich is that what Ferdinand and Tessa called the device manager, but I guess so. And yeah, for these bad schedules, we would want to apply, or we are applying mathematical optimization. And I wrote, or I'm currently writing, an adaptive scheduler and incorporate error management. By SiLA, there's a feature called error recovery feature. So you have a standardized way in giving options to recover errors and handle them, or automatically choose recovery steps. So these can integrate it in the schedule. Yeah, so what did we implement in particular? Yeah, I've brought you an example. I will show you a video of it later. So this is just a toy example. We have 2 containers. We want to read their barcodes, incubate them for different duration, measure the absorbance of one of them, and put them back. Then you have to describe this process. We decided for a Python-based description because that's quite easy readable by machines as well as humans. And Python has a built-in syntax you can exploit. I've also brought a more complicated example if you're interested, where you can really see why this Python syntax is so useful. So you can use loops, variable declarations, if conditions, custom functions, whatever Python has. So the workflow of this toy experiment looks like this. It's a bit hard to read, but this is also a step to check whether you defined the correct experiment you really want to run. And finally, this has to be scheduled on the platform and executed. And this is how a particular schedule could look like. Okay, so you can imagine how this looks. I made a video of this toy example. I only can hope that your connections are quick enough. I tested it with university internet and it works. So in the picture, so I just stopped it. Can you see it or is it too buggy?
You just stopped it.
Yeah, I stopped it, but before it,
Yeah.
could you see it
was
moving?
fine.
Yeah.
It was fine.
Okay, good. So in the bottom right, you see the screen on my laptop, where you see the supposed schedule of the steps. And the workflow graph, it turns yellow and green when a step is in operation and after it's done. So, oops, there it goes. So the upper one is how it's supposed to be, and the lower one is what actually happens. And this is 4 times the actual speed of the video. So you don't have to, so it gets becomes quicker. But actually, the robot has the capability of being twice as fast as you can see it. But it actually gets quite scary. What you can see is that it's not always the same. So sometimes the job is done before it is planned to finish. In that case, the scheduler could do a reschedule to apply a quicker one, or just let it just waste the time. Yeah, there you're seeing my laptop. Now it's going to be brought from the cytomat to the plate reader. And I'm going to stop here and make it a bit slower because this gets interesting. So currently you see a lid on this plate. This has to be removed for the absorbance measurement. And now you will see it takes off the lid and does some shaking. Because in the past, the plate got stuck to the lid when there's some glucose solution. This is something like a step we added, which could not be added with the commercial software. And now this plate has to be brought into the plate reader. And to organize this, we gave a feature to every device to interact with a robot. We called it robot interaction service. So the robot goes in a safe position near the plate reader. Then it tells the plate reader to prepare, in this case, bringing out the carrier. Then it goes down, places it. Then it goes back to a safe position. And then it tells, okay, I'm safe, and the device continues. This is quite nice with SiLA because you can access the same device from with several clients at a time. So the ARM server has a client for each device. Okay. Yeah, that's real. I'll skip the real experiment. And to our current status. So this was just a toy example, but we actually ran experiments. But so far with linear workflows, so no if conditions, although we can parse them. And our mathematical programming can, let's say medium-sized workflows can be scheduled, and all devices are controlled via SiLA. And the plan is to improve this scheduling software so we can exactly schedule even large workflows, which the commercial server just struggled with. Then there have to be, of course, excessive testing. So the last experiments worked, but I suppose there's still some hidden bugs. And I planned with Lukas from Munich to include this scheduling software into the SiLA manager, so include it as a microservice. So we have one GUI to run, to operate either every single device or plan whole schedules, and incorporates the error recovery service for every device. And then we will bring this solution to Berlin, which is, for time reasons, probably the last thing I will show you. I also brought you a small video of our mobile lab assistants in Berlin. So you can see in live what Adam described. So this is a mobile lab assistant, which will transfer a plate from one to another. It's, to be honest, quite sensible. So the kinematic software isn't that good. I think so. It sometimes gets lost in the lab. Here you see how it checks the barcode and then goes to the plate. And sometimes the arm goes into singular positions, or it runs into obstacles, so the whole device and stops. And yeah, now it will go through this diesen Gang. It has to be taught very carefully. So as Adam said, right now the status is that you have to teach every position by hand and model, yeah, that's my laptop, and model the environment so it doesn't get lost. So it's driving quite slowly to avoid these errors. And
but, sorry, Stefan, is it working at night on its own, or do you always have to have a person behind it?
So it's supposed to work on its own overnight. The last overnight experiment was 1.5 weeks ago, but it's still too buggy, so this kinematic software, that it's not safe. So effectively, the person has to be there in case it doesn't work. That's still the...
and then maybe sorry to interrupt you. Yeah. On your list, there was one other point where you wanted to use humans as SiLA service providers. That's very interesting, because that's what we also want to do. Can you comment on this quickly?
Yeah, so we have these two solutions for Berlin Lab or for a Greifswald Lab, where the robots look very different. And if you just imagine, you have, instead of a robot, you have a human. And you have, let's say, give him a tablet, which is running a SiLA server. Then you can send these movement commands to the tablet. So the human gets a message, okay, please transfer the plate from here to there on that position now. Then the human does a job, says, okay, I'm done, which will send on the SiLA way a command finished signal, and the process goes on.
Yeah. And how's the compliance? I mean, could you imagine that somebody does this 8 hours a day, just following commands from a tablet?
I have no idea. Do you have students? Would you like to do that? I mean, you could just place them, you could give them a desk in the lab, and they have to do this every, I don't know, 20 minutes, 2 hours.
Yeah.
So they can do other work and just get pop-up messages. Okay, please now transfer plate.
Yeah, it's a very interesting concept. I mean, we definitely have to talk about it, because we also thought about how to organize it. But yeah, thanks a lot for the very nice presentation. Yeah, I think we have to stop because Adam is having to leave. And yeah, I also have like question to Ferdinand and to Tessa, because their project was very representative for a university, for the academic university project. like the ones we are running here. And the question is always how to maintain it after the person who invented it. So how to keep it alive. Is it publicly available? Have you submitted it to a GitLab or GitHub or so?
Currently, our software is in our local GitLab repositories. Some published work on the university public available GitLab repositories, but the main part is currently in our local repository.
I mean, because we are currently undertaking very strong effort to bring the SiLA GitLab up to date and to maintain it, to get a professional maintainer, to make sure that the stuff, I mean, as you said, that it gets automatically compiled and it just works out of the box for people who are not so experienced. And I think if we don't bring our projects into this environment, they will die out sooner or later. So, but yeah. Anyway, thanks for the speakers. Thanks to the speakers for the very nice presentations. I'm very sorry that we don't have much time for discussion now. And as Adam invited everybody who's interested in robotics, which is probably concerning his presentation and Stefan's presentation, to continue in the robotics work group, which is posted into the chat. Feel free to do so. I will do so. And yeah, Tessa Ferdinand, I don't know if you will join. If not,
yeah, if you have any questions, just send us an email. That's totally fine.
Actually, all the emails are on the flyer. I think everybody got the flyer. So thanks a lot. And then I will end the session here and see you all soon.
Thank you. Bye.
Bye.
Yeah. Goodbye.
Bye.
Yeah. Thank you.